none of your group members were in lecture, then you should watch the video from the lecture. Is that fair? Okay, good. But I'm talking to the choir here, right? You guys were all here yesterday. Ooh, get through that now. That matters. All right. Today we're gonna talk about fixture design. Why? I mean, I know why. I'm wondering if any of you guys have any ideas. Nick always answers questions. Somebody else. See, I remember Nick's name because Nick always answers questions. Look at these borderline and that A-B. Okay. Okay.
Well, we don't have a basic rectangular stock.
All right. So we're understanding that we may need to design our fixture if our stock is a shape that's not like a block, really block. You can play with blocks in there, kids, or like Legos. Right? If our part looks different from a Lego, we might need a special fixture to hold on to it. So that's one reason that we'll talk about fixture design. What's the function of a fixture in manufacturing? Nolan.
Keep the part in place.
So, all right. So a fixture in manufacturing will keep a part in place. I'll buy that. Is that all a fixture does in manufacturing? Is keeping a part in place all that a fixture does in manufacturing? Okay, so by manufacturing, do I necessarily mean machining?
It can also move our part from one process to the other.
Oh, so a fixture could have some automation features built into it. Your fixture could, in fact, be a conveyor. So it's holding that part in place relative to the conveyor, but it could be moving the part along to the next process. I hadn't even thought of that one. Why else? I suppose I thought of it several times, but it's never expressed it in words. So fixture's gonna. What place does it hold it? It holds it in place, but in what place? All right, it depends on the part. I'll give you that. But regardless of which part you have, what place does it need to hold it in? Yes. Right. So let's say that it has to hold it in the correct place, right? And so what goes into being the correct place? Say if we're cutting a rectangular prismatic piece of stock in a milling machine, say one of the mini mills you get when you're in the lab. What goes into that being the right place? Up the back. All right, so the fixture itself has to not be within the tool path. And that can be an iterative thing. We say that we design we sort of design the tool path and the fixturing at the same time. So if we find out that in order to make the feature that we need to make, the tool is going to have to be at this location, well, then we have to know that there can't be no fixturing at that location, right? So, all right, so we're gonna consider whether or not the tool's going to interact with the fixture. Now, is it okay for your tool to cut the vice jaws in the milling machine? Is it ever okay for your tool to cut the vice jaws in the milling machine? Really? Anybody say yes? Be proud. It's always okay if you're doing it on purpose. Right? So sometimes we'll do, and so when we're cutting the jaws on purpose, regardless of the material the jaws are made out of and their hardness, we call those soft jaws. So we might make soft jaws out of tool steel, but we still call them soft jaws because we've intended to cut them. And so if I, for example, had a piece of stock material that looked like this, those wavy lines indicate that I cut it with a bandsaw. This is a very wavy bandsaw. And I want it to look like this. Let's say. And I'm intending to hold it in a vise. And my vise jaws on my vise are typically that big. So what would the process of cutting that have to be? If I want to clean up the wavy edges on my part, how could I do that? Go ahead. We should use an end mill, not a drill. We're going to move sideways. Okay. So what I could do is I could fixture it. So this sticks out one end of the vise, and I have my tool path to remove material over here. Then I can flip it over so that it sticks out of the vise. Oh, and again, remove material to the same spot, right? Now, if I'm going to do that trick, when I set so we've got tool and work offsets for both of these programs, right? And so let's say that the offset for the first time we run the program is right at the end of the stock material in the center. Anybody want to tell me what the sequence would be, how I would set that up? Set the work offset? If my workpiece is hanging out of the end of the vise here, the offset is on the end of the center. Anybody remember which probing macros we might use for that? Go ahead. So I can do X web. This is X, right? So I probably don't want to do X web. I do Y web to locate the center this way, right? And just X one direction to get the end. And then Z, what do they call it? Z? Probe Z surface only or something like that. So like probe X surface only, that'll locate the end of the part. Probe Y web will locate the center of the part in Y. Okay, so we successfully run our operation. Now, this edge has become straight. It's no longer wavy. This edge is wavy, right? What I'd like to do is flip the part over. Flip the part over. Now, this edge is the one we just cut, and this edge is wavy. And let's say my tolerance on this dimension, let's say this is 5 inches, plus or minus 1.001 inches. So I want that part to be 5 inches long, plus or minus 1/1000 of an inch. We've cut one end of it, so now that one end is square. Where should I put my work offset? So on the end that I already cut, since we did the other one in the center, we can put it in the center here. All right, so it can't be the same program that ran the first side, right? The program that ran the first side just cuts a little bit of material right away from the spot where the offset was. This program, we're going to put the offset over here, and we have to have that program set to cut 5 inches away from where the offset is, right? Okay, so all right, so we've got both programs. You guys were working hard in the lab, right? Yeah. See, we're going to do that. And you didn't bring any for the rest of us? I was actually, I was going to get every copy, but I didn't know what kind of copy you want. But it kind of doesn't come to my nose. But if I'm pressed, I do the dark first. So, all right, so I've got both programs. I've run the first program successfully. I've got my square n. I've flipped the part over. Does it matter if I rotate it around or flip it over? I hope not. Right? If we were doing other features, like if we had holes and if it was not square, then it would matter if I rotate it around or flip it over. But since it's rectangular, so it's square, I flip it over, I go to set the offsets. What do I have to set? I just ran the first part, it ran successfully. Did I mention I'm in a hurry? I got a lot of these parts coming. Anybody? Do I have to do, go ahead.
Well, you already have the Z segments.
The Z hasn't changed, right?
You're still in the setup for the Y.
The Y hasn't changed.
You just have to use X.
I have to do with X negative, X positive. I don't know if it's negative or positive. I look at the picture. Look at that, W family's calling me. What do they want? Right, so if you're flipping the part over like this, you only have to throw the X again, because you already know the Y and the Z haven't changed. And that's been tested. That's fixturing or setup, right? But you can't understand fixturing if you don't understand how to do the setup. So we'll talk about both of those things at the same time. All right, so we're fixturing the part to make sure that it's in the right place. How can we screw up fixturing in a manual? So I forget your name up in the corner. You said an answer, but I forgot what your name was. Brittany. So Brittany told us we could screw up by putting the fixturing material in the wrong place. Oh, there's another way to make this part, by the way. Hold on. That was how I started this story. I could just cut soft jaws so they're shorter than 5 inches. And I could just cut on both ends without having to set it up again. That's the other way to make this part. So Brittany says we don't want to cut our fixturing device on accident. Right? We've said that it's okay to do it on purpose. Caveat to that, if you do it on purpose in our lab, make sure you told the staff member your plan so that we agree that it's a reasonable plan. But yeah, we can cut the fixture. We can kind of do it on purpose. How else could we screw up fixturing a video? Somebody's working on their MQP and it's, I don't know, people in the room that are working on MQPs, I don't know if that as well. So we could put, so our mini mill has a work envelope, right? So we've got the table, and we've got the probe over here, and the way we commonly have them set up, there's a vise here, right? And there's a column fixture here. So, but these things are both to the table, and they can move. Frequently, if we have a big part to cut in the vise, we'll slide this over. It's completely out of the machine, but it's okay to slide it over. So we'll loosen the bolts, slide it over. Don't forget this step, hang the bolts again. Even if that's not the fixture you're using, the table's going to be moving, right? You don't have to been there and done that. Got plenty of dirty t-shirts to figure out how to put it in the door and got the fixture jammed up against it. So we can move these things around. So it's possible for us to move this vise over so that if there's an operation that happens over here on the workpiece, we put it in a place that the machine tool can't reach. Has anybody experienced that? You know, we get an alarm message that says something like X over travel R or Y over travel R, depending on which dimension you put out in. And so when you simulate on the controller, you get that alarm, you say, I put it in the wrong place. So our fixturing has to put the workpiece in the correct location. The other thing that's really nice, when we're doing a fixture like this, we could put a physical stop attached to the vise right there. So we put the first part in, we cut it, we flip it over and push it up against the stop, and now we don't even have to set the X offset again. You just have to run the X offset that's associated with the second program, right? So you can make this go faster by putting a little thing in here. And when we put a stop in there, like this, we're doing what's called kinematic fixturing. And so we know from our, and so these slides are all posted. Somebody asked me yesterday to make sure the lecture slides were posted. I did that. So I should tell you that I did that. If you go to ME1800.com syllabus, scroll down to the schedule page. So who we have? Oh, these. What do you think? I'll fix that while we talk. All right, but that's where they're posted, as soon as I remember to post them. So kinematics. So kinematics is the science of locating things. And so 3 points to find a plane, right? So if I need to set the angle of something, I could have 3 balls that sits on those 3 balls, and I've got 3 points to define that plane. So I can change the angle by moving this one. Right, so 3 points to find a plane. If we want to, so what are the points in this scenario that's locating my workpiece so that I can repeatedly put it back in there? So I've got to locate the z. How am I locating the z in this scenario? I should finish drawing the picture. Yeah. So my workpiece is sitting on parallels. And so if we look at the end of a vise, you guys have seen parallels, right? You had to do something with parallels in the lab? Yeah. So if I'm looking at the end of the vise, we got my vise jaw that sits on the bed of the vise. Okay, there's a piece here, there's a piece here, and there's the little thing that we turn, right? To give us one mechanical advantage, we turn the screw. So when we put our workpiece in there, we put these little do-jobbers in that we call parallels. What's the function of the parallels? So we would like, in many instances, to not have all of the workpiece buried down inside the vise. Maybe because we want to cut along this edge. And if we're cutting along that edge, then we won't be able to get the tool in there down inside the vise. Right? So we want to Brittany, right? That's good. I remembered. Oh, it's been like 10 minutes. I'm excited. Brittany doesn't want us to cut the vise on accident, so we need to raise it up on parallels. So it keeps it up out of the vise. It also keeps it level, somebody said? Level relative to what? Right, so if you put it in there, you can eyeball it to be even with the top edge of the vise jaw, maybe that's your reference that you can see, really. Top edge of the vise jaw is not necessarily perpendicular to the motion of travel. It's not necessarily parallel with the machine tool. So what we got to do, so our parallels are intended to keep both sides of this part the same distance from the table in the machine tool. So this is the table. Vise body. Right? And so our parallels, so how could that go wrong? Because what's going to happen if our part's not flat, not parallel? Yeah. If we machine the Z-surface, the top and the bottom won't be parallel to each other anymore. We're here in this program, we talked about really machining the X positive face, really machining that face, but we're going to end up with a part that looks like this, right? when we look at it from the side, it's going to be hopefully not that badly. But if we tip the piece like this, if we tip the piece this way, we may not notice it in this program. Except, where's the clamping force applied? Clamping force is applied by the vice jaws here and here pressing on it, right? The vice jaws here and here pressing on it. If we put it in like that, we don't have as much clamping force, right? We may have the same force, but we certainly don't have the same pressure. And the part could pop up out of the fixture. So, what are the failure mechanisms using parallels, using a vice like this on the table? How could it become unflapped? Because it happens all the time.
If there are chips in the roll.
So if there's chips underneath this one, no chips underneath that one, chips here, no chips here, right? So that will make your part sit unflat. What else could go wrong?
If they're not flush with the bottom of the vice.
So if they're not sitting on the bottom of the vice, maybe one of them is, one of them isn't. So we fixed the chip problem by cleaning it first, right? Now, you can play with this interface all day long. If there's chips here, you're never going to get it right. The vice could have chips underneath it. Those vices sit on the table for weeks at a time sometimes. Sometimes we find them, there's a bunch of chips underneath it because whoever put it on the table wasn't careful. So if you're cutting a part, you don't really care if it's a little bit askew on those things, then it doesn't matter. But if you're cutting a part for your MQB and you care, we especially care if we're cutting that part and we're flipping it over and we want the features on one side to line up with the features on the other side, we can really screw it up by doing this. So we got to be careful that everything's clean. The other thing, so if it's clean, it will be straight and it won't, it'll have the maximum clamping force possible. All right, so that's a good thing. That's something we can screw up. The other thing we can do is we can have this vice twisted on the table like that. And then our finished part would look like this. Unless we flip the part over the other way, in which case it would look like this. Right? So we can make parallelograms of trapezoids all day long when we flip our parts over if the vice is crooked on the table. Anybody know how you could check to see the vice is straight on the table? We don't do this in ME1800, but you guys can figure it out. Go ahead.
You use a level.
So for this orientation here, you could use a precision level. Because when we set up the machines before we put the vice on it, we put a precision level on this table, and you can actually adjust, there's little feet the mills sit on. You can adjust the tension in the casting, so the stresses in the casting, by adjusting those feet, and you can actually twist that table. So we level the table. So you could put a level on it for that. What about skewness this way? How do we fix that? So we did in ME1800, we don't use the style indicators that are on the machines, do we? I don't think we ever use them in ME1800. There's a little thing that's got a red magnetic base. It comes out from the machine. It's got a little needle on it. The needle's attached to a gauge that spins around. As you move the needle on the gauge moves. So you attach that to the spindle. You jog back and forth with your indicator needle in contact with the vice and see if it deflects. So you can actually align that. And that process is called framing the vice. You get to do that as big as you can. All right, get at it. So kinetic fixturing. This is what we talked about yesterday, right? So we've got to have enough force to hold the workpiece in the machine tool. And so if we're so we got our building part. And then we do this. That's the forces in this direction, right? That it's spinning around. right? And so we want to do a worst case scenario. So we either assume the force is all the way up or all the way to the side along the direction that it can slide, right? And so what's our maximum cutting force that we can have? What's the maximum? So we can figure out the maximum cutting force, and then we can see what's the maximum power we want to allow. We could actually set those machines to stop, to alarm out if the power exceeds a certain threshold, and you can set the threshold.
It should be more than the frictional force.
Right. So there's some maximum frictional force that's possible based on the normal force and the coefficient of friction, right? And so if our cutting force exceeds the maximum possible friction force, the part flies out of the laser. That's what it sounds like. Somebody's been here when the part flew out of the ice. It's louder, right? Okay. And we talked yesterday about the problem with the spinning jaws on the lathe. Right? We talked about that yesterday. Everybody's got that in their mind. So fixturing, hold the piece in the right place, and make sure that we have sufficient force so that it doesn't fly out of the workpiece. Sorry, fly out of the G-tool. What's bad about it flying out of the G-tool? So what? So what happens? Like what? All right, so we could break the glass. Oh man, we got trouble for that. The ME department was moving noise and it cost $140 to ship that piece of glass. I'm like, you drive to California and go pick it up. Right? I think $140 is actually a pretty good price for that giant piece of safety glass. But we did decide that we're going to look for a local source. Since the day after the news, maybe I put in some of the chips with the pieces. Not because of direct type of ice though. It was because he plunged his end mill into your steel part. What happens when we plunge a tool into a steel part? Any part, I don't know, butter part. What happens when we plunge the tool into the part? I think we tell you in many instances not to plunge the tool into the part of the lab. When you're doing the cam and stuff like that. I don't know that we sufficiently explain the reason not to. This is one of those things when you yell at your kids, don't do that! And you don't explain to them, it's because I don't want you to find the bus. Or because, you know, it's urgent to get the don't do that part out there. So why don't we want to plunge? Think through the physics of chip formation.
Are you talking about end mills?
Yeah, plunge an end mill into the workpiece.
Let's not make the cut in the direction.
So we probably say that in the lab instructions. They're typically not intended to cut in the Z direction. Why not? Why don't you make end mills that are intended to cut in the Z direction?
Is that what a drill mill is?
So the drill mill is in fact an end mill that's intended to cut in the Z direction. Okay. So what's the physics of the chip formation as we look at the cross section, the bottom face of the end mill? So what causes the cutting again? Right, so rotation causes cutting to happen, right? In both milling and turning, it's rotation that causes the chip to form. So it's the rotation of the cutting tool, right? So our cutting force goes like that, or the rotation of the workpiece, and I'm not going to lie down on the table all over. Right, or the rotation of the workpiece. Right, that's what causes the cutting to happen. So the surface speed equals what? The circumference times RPM times. Then you get converted to the right units. Right, so what's the circumference at the center of the end mill? 0, because the diameter at the center of the end mill is 0. So as you move in along the cutting edge, so there's a flute at the bottom of most of those end mills. It's not like they don't have a cutting edge on the bottom. Right, if we look at the bottom of one of those end mills, we're using 3 flute end mills. It looks like this. And so this is a sharp edge. There's a rate There's a cutting edge there, a right face on it, there, and there. And so the surface speed here is the spindle speed times the diameter of the end mill convert the units times pi, right? But the surface speed here is 0. And as you get closer and closer to the center, it approaches 0. So it's not cutting anymore, right? If there's no surface speed, it can't cut. What does it do though? Because it feeds in, it's got to sort of mush the material out of the way. It's got to form the material instead of cutting. Don't worry, it can form the material because there's plenty of heat. Right up until the end mill goes explode. Right, so that's why we have you ramp in or spiral in if you have to come into an area, or you can drill a hole. So why does the drill work? It also has 0 surface speed in the center, right? So they make that sharper tip that actually puts a chisel on it, and so that's actually intended to do a little bit of cutting from the feed. It's got a cutting edge. It's intended to cut a little bit through the feed. And what else happens when we put a sharp point on our tool and we press with the same amount of force? Well, if we push with too much force, I'll agree the tool breaks. If you put a sharp point on something and you push with too much force, it breaks. But do we like a sharp knife or a dull knife? Sharp knife tends to cut better with the same amount of pressure, right? With the same amount of force. Because the pressure goes up, because that stress that we're putting on the material is higher when we have a smaller surface area, right? So that drill is designed to actually cut material on that tip as it's got 0 surface speed for spinning. So that helps us a lot. So yeah, if you plunge and you plunge too fast, it will explode, chips the window. No, 350 plus shipping. So, all right. So we're making our parts. We're gonna identify the features. We identify the things we want to make in the part, right? We create our tool path. As we're creating our tool path, we have to understand the fixturing, how we're going to hold the part, where we're going to define the origin on the part. The first exercise, when we're flipping the part over, it mattered where we put the origin, right? Because if we tried to make them 5 inches long, we kept putting the origin out here on this side, how would we make it 5 inches long? You could do it, but how would you do it? Cut, check, cut, check, cut, check, right? So you'd have to iteratively approach it. Figure out our tool paths, we put everything in the machine tool, we can make our finished parts. Okay, so somebody at the beginning, I think it was Michael, right? I think Michael said we might have parts that don't look like this. Right, that was the very beginning. I said, why do we need to study fixturing? Because not all parts are going to be square. And I wanted to get to that, I just wasn't going to get to it first. So, let's say we have this part. This is a drawing for a part to be made for an MTV. I will admit I was involved in making this, and in fact, when I used to think I had help these make this up. This is back when I thought I used to think that I had to help students make their parts by making their parts for them. So I got to make this part. I learned a long time ago that if I help students learn how to make their own parts, then I'll have a lot more students make their parts. They fix the dynamic. Because this is the part. What's the first thing I did when they came to me with this part? They said they needed this part for their MTV. It's got some unique challenges. What's the first thing I did when they brought me this drawing? Yeah, maybe on there. I like cropped the drawing and put it on the thing. So I think they told me the units. At least I asked them. These are inches. It would have been a real small part they were millimeters on.
You may have asked what material they wanted.
So they told me they wanted aluminum, so that information is there. First thing I did was try to talk them out of this shape. I didn't want to make this shape. What's challenging about this part? There's pretty much no two perpendicular or parallel surfaces, right? These two edges are parallel to each other. So I can clamp on that, I suppose. But there's pretty much nothing to hold on to when we make the part. It's aluminum. Go ahead, Andre.
I was thinking, so what you're saying is that you can't really hold on to it because
well, if I tried to
from the
clamp
side,
it,
you might destroy the one of the clamps.
yeah, so if I tried to clamp it from here to here, I'd have pretty low cutting force and it would be uneven. It would be hard to keep it level with the machine. If I tried to clamp it on the sides, I wouldn't be able to access the sides to cut it. You'd have to clamp way down here, and then the rest of that would be sticking out like the Loch Ness Monster. Or sticking up out of there like the Loch Ness Monster. And so this piece would do a lot of that while I was cutting on it. Yep.
Was the piece of aluminum provided and you had to cut the features into it, or was it just a rectangle?
We came up with the stock. We actually cut it out of a piece of stock that. So we cut it out of a rectangular piece of stock that was about that big. I'll give you that. That was about the piece of stock I cut out of in that orientation. I think. Wait, no, not enough. In that orientation. So any ideas? So if I tell you that's roughly what my stock looks like and this is what the part looks like, how would you start? Go ahead.
So I might start by like putting, that silhouette into the top of the part without, putting all the way into it, as far as the width of the part. Then I could, that would be really good. And
so if my stock material was plenty thick, what he's saying to do, if my stock material is plenty thick, we define a pocketing operation where this is an island that sticks out of the pocketing operation. And we remove all the materials and we make a plane below it, and our part is now sticking up out of that plane as a boss. And then you're going to flip it over.
Well, that's what I was also going to put away from like the space around the part that from the top of the common angle.
From in this orientation?
From the from that orientation, I've also cut some
oh, so you'd like do a surfacing operation here and remove some of this material?
Actually, yeah. What I mean is I like also got a little space around it to make room for when I have to flip it.
So you cut it, but you go deeper than it is, so that you can flip it over and remove the material. Yeah. Okay. All right. That is not how I made it. That's not a horrible idea. I didn't think of that. Go ahead.
You made it the way that he mentioned. When you flip it over, by the time you finish doing the contouring operation, wouldn't it just fall?
Well, if you held on to the outside part, yeah.
How could you clamp it to the actual part itself, or half of the part?
What if you took some of those fancy soft jaws I talked about, and you machined the mechanisms into them, and then clamped it like that?
That would work.
That would work. That's not what you do. But it's what we do frequently when we use this method to cut parts. And so when you cut your base, we use this method to cut parts, right? Except our base doesn't have weird geometry, so we just clamp onto the base and left over. We flip it over and we face off what was left.
we'll work on it, go off this contrary idea, contrary to these, all the way through the interconnected device. Pieces of metal every so 7 inches.
That's very similar to what I did. So this picture down here, what I did. Right, here was our part. There's the part. There's my first operation, and so I had my box. I defined a pocketing operation over here that made this part of it. I defined a pocketing operation over here that made that part of it. But I didn't have to have a piece of stock material that was significantly taller. Your method requires a little bit extra meat to hold on to. And we use that a lot. I didn't use it with this part. Now I can get a piece that was actually just the right dimension this way, so I didn't have to machine those two faces. We didn't care what the surface finish looked like there. Then, so this was that process finished. Then we took it to a bandsaw. And we cut that off. We cut that off, so this is longer than it needed to be. We stuck it in the mill with this end sticking out and the shelf part facing up. So just that little part sticking out of the machine. Put the end on it, put the hole in it, made the shelf. That allowed me to have the sharp edge of the end mill with that feature, so I could get a. So with the method that you were going to do there, we went all the way around it like that. We would still have to put it in to clean up that edge because you're going to have the radius of the end mill. It would be the minimum radius that you could put there. Yep.
How did you make that shelf?
Say again?
You said that
so
you drilled the hole, but then how would
I
you
should
make
make another one of these parts so I can bring it into class. So I put it in with it flipped upside down from here, and this end from here is sticking out at the end of the
okay.
vise.
Okay. So you get the
So I can
sharpness
have
of
my
that
end will just come by with a contour there, and then the contour around the end and drill a hole. Then we said, hey, we must have done that operation last. First, we cleaned up this end by sticking that out of the vise, making it square. So when I do this operation, I use that for my X reference, so I get the correct length on the part. So sometimes we have to think about our fixturing. Yeah.
Since you said that you cut it with a bandsaw, the lengths were more than what they needed to be.
Yeah, we made that first piece bigger than we needed to.
So when you clamped it in, how did you know how much material to remove to get it to the right?
Yeah, I was
Wing it.
pretty sure they didn't have any method to measure if I did it right. But if it mattered, you'd have to have some way to get a reference from here, right? Because if this dimension mattered, you'd have to be able to identify that change and get that measurement. Over here, the dimension that like the location of the hole was important, and making it pointy on the end was just for aesthetic purposes. But the distance of the hole from the shelf is what matters.
Okay.
So yeah, I was winging it then, but that's a thing to consider. All right, so how else might we hold a non-standard shape? That was one way. So what I did is I left extra workpiece material to hold on to while I was cutting it. Same as Deb's method was to leave extra workpiece material to hold on to while you're cutting it. You could have a fixture plate that looks like this. So the gold color, the titanium part there is the workpiece that we're fixturing. And so we use these clamps, and we can put something under it. We can clamp down to it to make it, so we got pins there to locate it, 3 pins located in X, Y. To locate it in Z, we have these little rocking flat surfaces where they will orient and conform to the surface so you don't bend it. So you can design elaborate systems of clamps like this. We have all those kind of materials downstairs. So you need to clamp something. Now, we care about friction force, right? What other kinds of forces can hold our workpiece in place? Yes, magnetic. We could use magnetic force. If this works, it's the next slide. Amazing. It's actually a company in Worcester that makes magnetic fixturing tables, where they've got a bunch of permanent magnets. So you can do them with electromagnets also. This type of table has permanent magnets in it. But if you put a bunch of permanent magnets in it next to each other, and you rotate, so you get South Pole, North Pole next to each other, the magnetic field goes away. You rotate it back, the magnetic field comes back. Magnetic field goes away, magnetic field comes back. So you can have permanent magnets that you turn on and off. That's cool. Right? And so there's this lever in here. So you flip the lever, and what it's doing is it's rotating some of the magnets throughout swivels. So you turn the magnetic field on and off. That's kind of cool. The one we have actually has a solenoid that pushes it instead of a lever, and it takes 480 volts at 3 phase and 60 amps to operate the solenoid. It's a lot of power to flip it over. There's tremendous magnetic field available. There's a whole control unit that turns it on and off. The one we have, they actually give it to us as they call it a consignment, but really it's a gift. So that we can demonstrate it to you guys. They give them a Walker magnetic chuck there. They had a customer in the field that their control unit had failed. So they said, we need to build a new control unit for them. Can we borrow the one that you have, let our customer use it while we're making a new one, and then we'll swap it? I said, sure, no problem. They come over, take it out. The fixture was on the table of the milling machine. The magnet was turned on. They took the control unit and left for like a month. And that milling machine sat there. With a really powerful magnet sitting on it. It could do anything else. If you put something on that magnet, you weren't taking it off. So, my advice is, if you loan somebody the controller for your Walker magnetic chuck, turn the magnets off first. Then at least because you didn't take it off the table either, it was magnetic to the table. When you do this, you gotta be careful because that magnetic force, you still only have friction now between the bottom of your workpiece and the table. And the table's pretty smooth, so it doesn't offer a very high friction coefficient. So there's actually holes in it where you can put pins in. So you can locate the XY and counter XY forces with pins, and use the magnet to hold it down and counter the pulling it up force. Fixture design. You can use fixturing for all kinds of things. There's words on some of the slides you can read if you want to. And before I walk away, I'll actually copy that. Yeah, dude. It went on before I left class. Those guys at the ATC lied to me. I said you have to select all the groups and put them in, and then the group submission for all those groups. And they said if you selected no groups, it's available to any group. They lied to me. I'll fix that right now while I post these notes. And so nobody's going to be penalized for handing it in. Not yesterday. Okay. Could you please hand it in to the submission? Otherwise it'll get lost. So you must have all figured that out yesterday. So when I checked the discussion board this afternoon, that would have been a good thing. Dan was saying it last time. I just like find where yeah, okay. Are you putting on the assignment? Yeah. Okay. Thank you.
What?
I gotta get on the TV.
Hurricanes through me.